In statistics, we are mainly interested in the value of a population parameter, such as a mean or variance. However, we rarely have data for the entire population and must estimate a parameter from sample data. If we draw a random sample from the population, we can use the data to estimate the population parameter. However, if we draw another random sample and compute another estimate of the population parameter, we will get a different value because of chance alone. Each time we sample from the population, we get a new estimate of the population parameter because of sampling variability. The standard error of the estimate quantifies the amount of sampling variability. In addition to computing a parameter estimate, we would also like to know about the precision of our estimate. That is, we would like to know a range of plausible values for our parameter. We do this by computing a confidence interval. A confidence interval provides a range of values that likely contain the population parameter of interest. A confidence interval is computed by adding and subtracting the margin of error from a point estimate. The margin of error describes the precision of an estimate to a certain degree of confidence. The smaller the margin of error, the more precise our estimate. As an example of the margin of error, you have probably heard news reports that say something like, the president's approval rating is at 42% with a polling error of plus or minus 3 percentage points. The error to which they refer is the margin of error. It tells us about the precision of an estimate to a certain degree of confidence by taking sampling variability into account. The margin of error is composed of two parts, the critical value and the standard error. The critical value is chosen according to a researcher's desired level of confidence, and the standard error reflects the degree of sampling variability associated with the statistic. Thus, the margin of error and subsequently a confidence interval is affected by the confidence level and the sample size. Let's focus on the confidence level first. The confidence level describes the percentage of times the interval will contain the population parameter if we repeat the process of sampling and constructing the interval. There is an important nuance to this definition that we will revisit later. For now, we will look at how we set the confidence level. You have complete control over the confidence level because it is a function of the significance level alpha that is set by the researcher. For example, for a given alpha level, you have a 100 times 1 minus alpha % confidence interval. For example, an alpha level of 0.01 results in a confidence level of 99%. An alpha level of 0.05 leads to a 95% confidence interval, and so on. You choose the confidence level, but your choice will affect the size of the interval. A greater amount of confidence means a wider interval. This figure shows 4 intervals. Each one is based on the same data, but the level of confidence has been changed. The smallest interval is at the bottom, and it has a confidence level of 68%. The next largest interval is the 90% confidence interval. The largest interval is at the top, and it has a 99% level of confidence. This effect may seem counterintuitive. You may think the interval should get more precise as the confidence level increases, but it doesn't. The interval gets wider as the confidence level increases. Think of it as fishing with a net. The bigger the net, the greater the confidence in catching a fish. Sampling variability is another factor that affects the margin of error and size of a confidence interval. The standard error quantifies sampling variability, and it is a function of sample size. Look at the confidence interval for the population mean when the population standard deviation is known. The standard error is the population standard deviation divided by the root of the sample size. Thus, as sample size increases, the margin of error and the width of the interval decreases. To see this effect more clearly, here are 4 intervals, each computed from 4 different samples, each of a different size. Keep in mind that all of the intervals are 95% confidence intervals. Notice how the widest interval has the smallest sample size and the narrowest interval has the largest sample size. By designing studies that have large sample sizes, we can increase the precision of an estimate. You can think of very precise parameter estimates as the statistical version of high-quality manufacturing. Earlier, I mentioned an important nuance to the definition of the confidence level. Understanding this nuance is key to proper interpretation of a confidence interval. A confidence interval does not tell us the probability that a parameter is in the interval. Rather, if a random sample of size n is drawn from the same population and a 95% confidence interval is formed from each sample, then 95% of the intervals will contain the population parameter. That is why we may say that with 95% confidence, the parameter is between the lower and upper bound. We use the word confidence, not probability, when interpreting a confidence interval. It is incorrect to suggest that the interval gives us the probability of a parameter. This slide shows two incorrect interpretations of a confidence interval. In the frequentist paradigm, we think of repeating an experiment over and over again to obtain a sampling distribution. We do the same for an interval estimate. The next animation shows the process of drawing a random sample and constructing a 95% confidence interval. If we repeat this process a large number of times, then 95% of the intervals will contain the parameter. In this animation, the dot shows the point estimate and the horizontal line shows the confidence interval. If the interval is blue, it contains the population parameter for a mean of 50. If the interval is red, it does not contain the population parameter. We should see that 95% of the intervals are blue and 5% are red. The correct interpretation of a confidence interval should be clear now. There are a few more important points to make about a confidence interval. First, a confidence interval is about a parameter, not a sample statistic. This point is confusing because we use the sample estimate to construct the interval. However, the interpretation is about the parameter. Notice that it is the parameter that falls within the lower and upper bounds a certain percentage of time. Next, there is a direct relationship between confidence intervals and hypothesis testing. The type of interval we create is aligned with the alternative hypothesis. For a two-tailed test, we construct a two-sided interval. For a one-tailed test, we construct a one-sided interval. The way we construct a one-sided interval is a little tricky. For a lower tail test, we add the margin of error to get an upper bound. For an upper tail test, we subtract the margin of error to get a lower bound. Once we construct an interval, we can use it for hypothesis testing. If the parameter given by the null hypothesis is not contained in the interval, we reject the null hypothesis. So we could skip the hypothesis test altogether and just construct a confidence interval. In summary, confidence intervals provide plausible values of a parameter. They give us an idea about the effect size because of how far away the interval may be from the value under the null hypothesis, and they describe the precision of an estimate, which is given by the width of the interval. It is best practice to construct a confidence interval whenever you are doing hypothesis testing because of the extra information that it provides.